Hi everybody, in this recording we will be going over section 4.4, the fundamental theorem of calculus. So everything we've built in the previous sections leads to this very important theorem, the fundamental theorem of calculus. So if a function, lowercase f, is continuous on the closed interval from a to b, and capital F is an antiderivative of lowercase f on the closed interval from a to b, then the integral from a to b of f of x, this function, with respect to x, is equal to our antiderivative, so capital F, evaluated at b, minus our antiderivative, capital F, evaluated at a. So the integral of this function from a to b is equal to the antiderivative evaluated at b minus our antiderivative evaluated at a. So this theorem relates differentiation and integration directly, so hence the name, fundamental. So it essentially states that integration and differentiation are inverse operations. We have the proof of the fundamental theorem of calculus. So we let delta be a partition of our closed interval from a to b. So a will be our first point, x naught, and then we have all these endpoints. And our last one will be our x endpoint, which is the other boundary of our interval, which is equal to b. So we can write that the antiderivative evaluated at b minus the antiderivative evaluated at a is equal to the antiderivative evaluated at our xn term minus our antiderivative evaluated at our xn minus 1 term plus our antiderivative evaluated at each of these partitions. So we are just taking our xn minus our xn minus 1. So the last term minus the previous term and so on up until we get our first term, the x naught. So f of x1 minus our f of x naught. So the shorthand form of that would just be taking the summation from I is equal to 1 up until n of our antiderivative evaluated at our xi minus our antiderivative evaluated at our xi minus 1. So by the mean value theorem, there exists a number ci in the ith subinterval such that the derivative of our antiderivative, so f prime of ci, will be equal to our antiderivative evaluated at xi minus our antiderivative evaluated at xi minus 1 divided by xi minus 1. So we notice that our antiderivative, the derivative of that, at ci is equal to our function f evaluated at ci. And we let delta xi be equal to xi minus 1. So to obtain our antiderivative evaluated at b minus our antiderivative evaluated at a, we have the summation from I is equal to 1 up until n of our function evaluated at the point ci times our delta xi. So this is a Riemann sum that works for any partition. Now since f is continuous, it is integrable, and the norm of the delta x as it approaches 0, the limit of the norm as it approaches 0 of the summation from I is equal to 1 up until n of our function evaluated at ci times our delta xi exists. So that means that we have the antiderivative evaluated at b minus our antiderivative evaluated at a. Now taking the limit of our Riemann sum, that is equal to our integral from a to b of our function with respect to x. So we see that the proof of the fundamental theorem of calculus is simple and straightforward. And that is because the previous definitions and theorems were carefully constructed. So if you can find an antiderivative of f, it is straightforward to compute the definite integral. So for a majority of the time, we will no longer need summations because of this very important theorem. And the theorem is once again stated here. So we are taking the integral of our f of x with respect to x, and we are evaluating at the limits a and b. So that is equal to our antiderivative evaluated at b and at a, which is equal to the antiderivative evaluated at b minus our antiderivative evaluated at a. So the constants of integration are not necessary for definite integrals. So we see that when we take the integral of this function, we have the antiderivative plus c evaluated at b and at a, which once we expand, we have f of b plus our constant of integration minus f of a plus our constant of integration. When we carry out this difference, we see that the c's will cancel out c minus c, and we are just left with f of b minus f of a. The previously developed anti-differentiation techniques to evaluate these definite integrals. So first, we will integrate. So for this example, we have the integral of x cubed with respect to x. So the integral of that will be x to the 3 plus 1 divided by 3 plus 1. So that is x to the power of 4 divided by 4. So we have our antiderivative, and now we need to evaluate at the limits. So we are evaluating our antiderivative at 3 and at 1. So we plug in a 3 anytime we have an x in our antiderivative, and a 1 anytime we have an x. So that'll be 3 to the power of 4 divided by 4 minus 1 to the power of 4 divided by 4. And that'll simplify to 20. Now for our second example, we have 3 times the square root of x, and we are integrating with respect to x, and we are evaluating at 1 and at 4. So the square root of x in exponent notation is x to the 1/2. So integrating, we will have x to the 1/2 plus 1 divided by 1/2 plus 1. So that is x to the 3 over 2 times 2 over 3. And then we also need to multiply by this 3. So the 2 over 3 and the 3's will cancel out, and we'll just be left with 2 times x to the 3 over 2 for our antiderivative. And now we need to evaluate at our limits. So capital F of 4 minus capital F of 1. So once again, we plug in a 4 and a 1 anytime we have an x in our antiderivative. So f of 4 will be 2 times 4 to the 3 over 2, and f of 1 will be 2 times 1 to the 3 over 2. And we are subtracting them, and that leaves us with 14. Now our last example, we have the integral of secant squared x with respect to x, and we are evaluating at 0 and at pi over 4. So the integral of secant squared of x is equal to tangent of x. So that is our antiderivative, and we are evaluating at pi over 4 and at 0. So capital F of pi over 4 is tangent pi over 4 minus capital F of 0, which is tangent of 0. So that gives us 1 minus 0. So that means that the answer to this last example is 1. Now we will be going over the mean value theorem for integrals. So if a function f is continuous on the closed interval from a to b, then there exists a number c inside the closed interval from a to b, such that our integral of our function f of x with respect to x evaluated at a and b will be equal to our function evaluated at that point c times b minus a. So our proof goes as follows. If f is constant, then the equality will hold for any c. So let's assume that f is not constant. So by the extreme value theorem, f has a minimum and maximum value. So that'll be f of m, lowercase m, that'll be our minimum value of f on the closed interval a to b, and f of capital M, that'll be our maximum value of f in our closed interval from a to b. So that means that our function f of x will sit between our minimum and our maximum. Or in other words, our minimum will be less than or equal to f of x, and that'll be less than or equal to our maximum. Now, because integration preserves inequalities, we can take the integral of each of these three terms. So we will have the integral from a to b of our minimum value. So this is a constant. This is just a number since we are already evaluating our function at this m point. So we have the integral of a constant with respect to x. That'll be less than or equal to our integral from a to b of our function f of x with respect to x. And that is less than or equal to the integral of our maximum, so another constant right here with respect to x, and we're evaluating at a and b. So since we have a constant right here, we know that the integral of a constant is just the constant times whatever variable we are integrating with respect to. So here it'll be x. So we have f of m times x for our antiderivative, and we have limits, so we will be evaluating at b and at a. So f of b will be f of m minus b, f of m times b minus f of m times a. So we can just factor out the f of m, and we'll have b minus a times f of m. So this is the antiderivative of this term right here. That'll be less than or equal to the integral from a to b of our function with respect to x, and then once again repeating the process for this term right here. So we have the integral of a constant. This case is our maximum, so it'll just be f of capital M times x. And we are evaluating at b and at a, so we will just get b minus a times our constant f of capital M. Now we can isolate our f of lowercase m on the left-hand side, and we can do so by dividing by b minus a on both sides. So we will get that the minimum value, or f of lowercase m, is less than or equal to 1 divided by b minus a times our integral from a to b of our function with respect to x, and that is less than or equal to our maximum value because we divided by b minus a on all of these three terms. So for these two terms, the b minus a goes away, and with this middle term, we're left with 1 divided by b minus a. So by the intermediate value theorem, there is a c such that our minimum is less than or equal to our function evaluated at c, and that is less than or equal to our maximum. So our function evaluated at c sits between our minimum and our maximum values of f in the closed interval from a to b. So that means that our function evaluated at c will be equal to 1 divided by b minus a times our integral from a to b of our function with respect to x. The average value of a function is the number that is guaranteed to exist if f is continuous in the closed interval from a to b. If a function f is integrable on the closed interval from a to b, then the average value of f on the interval is denoted by f inside of these chevrons, and that is equal to 1 divided by b minus a times our integral of f of x with respect to x evaluated at a and at b. So as an example, let's calculate the average value of our function f of x is equal to 3x squared minus 2x in the closed interval from 1 to 4. So we know that this function is continuous in this closed interval, so that means that we will be able to find our average value. So that'll be 1 divided by b minus a, so b is 4 and a is 1, so we will have 1 divided by 4 minus 1, which is 1 divided by 3. Now we can integrate our function, so that'll be 3 times x to the 2 plus 1 divided by 2 plus 1, so that'll be x cubed right here because the 3's will cancel out, minus 2 times x to the 1 plus 1 divided by 1 plus 1. So x squared divided by 2 times 2, so the 2's will cancel out. So we are left with 1/3 from this term right here times x cubed minus x squared, and we need to evaluate at our limits. So that will yield 16. So our average value of our function on the closed interval from 1 to 4 is 16. Now we have the second fundamental theorem of calculus. So if a function f is continuous on an open interval I containing a, then for every x in the interval I, we have that the derivative with respect to x of our integral from a to x of our function f of t with respect to t is equal to f of x. So we let a of x be equal to the integral from a to x of our function f of t with respect to t. So from the fundamental theorem of calculus, we have that a prime of x is equal to f of x. So that means that a of x is an antiderivative of f of x. So now we let capital F of x be an antiderivative of f of x. So then that means that a of x can be written in the form capital F of x plus c, where c is some constant. So evaluating a of x at 0, that means we are taking the integral from a to a of our function f of t with respect to t, and that is equal to 0. So that means that our constant is equal to negative f of a. So that means a of x is equal to capital F of x minus capital F of a. So our antiderivative f minus our antiderivative f evaluated at a. Now if we take the derivative of a of x, that is equal to f of x, because we stated previously a prime of x was equal to f of x. We established that integration and differentiation are inverse operations. So in other words, if we take the integral from a to b of our function f of x with respect to x, that is equivalent to evaluating our antiderivative at b minus evaluating our antiderivative at a. So this can be written or rewritten as the integral from a to b of the derivative of our antiderivative of x with respect to x. And also that will be equal to our antiderivative evaluated at b minus our antiderivative evaluated at a. So as an example, we have the integral from -3 to pi of the derivative with respect to x of ln of x times